Video, we're discussing tensor parallelism as the continuation to our previous discussion in data parallelism. So we already have charted parameters, gradients, and optimizers with zero, aka zero redundancy optimizer, but we did hit a limit in terms of activations because that memory has overtaken our budget. If you look here at our previous graph, the activation is dominating even though we're in zero optimizer 3, which is incredibly optimized already. So let's look at tensor parallelism, which leverages the mathematical properties of matrix multiplication. So let's look first at some fundamental equations that make parallelization possible. So you can write a matrix multiplication as AB, or A dot with all of the rows of B, or the columns of A dotted with the rows of B. And this is what we said here, either by multiplying each column of B or multiplying each row individually and combining the results. And this is with A. So these are two ways that we're going to split up matrices in order to compute them on different GPUs. And as just an aside, we have our matrices represented as X and W in a neural network, where X is the input or activation values. So activation values literally just means it's not the raw input, but it's the input from a previous layer. Because once it has entered the neural network, then we call those intermediate outputs activations. And then W is simply the weights. And in this case, we are doing a NN linear, which is just a weight matrix plus a bias. Okay. And we will understand how we can take advantage of these matrix properties, first of all, with an intuitive example where we have the input X 4x2 and our weight matrix W, which is 2x2. And you can do the weight matrix input matrix multiplication simply on a single GPU in the following manner. But let's say that we have a really limited GPU and it doesn't fit, or we want to parallelize this calculation. So the tensors will be split into n shards along a particular dimension and distributed across n GPUs. And one thing we'll see in the following demonstration is that choosing row or column sharding requires different communication primitives. So we're going to start off with column linear or column-wise sharding, which means that we shard on the column. So you can see here the input becomes, or rather the weight matrix becomes two columns of 2x1 from a 2x2 matrix. So what we do here is we copy the complete input matrices to each worker. So each GPU has the complete input, but then we split the weight matrix into columns, and the inputs are then multiplied with the partial weight matrices, and the results are finally combined using an all-together operation. So this explanation is better served through the example. So we broadcast each input to the GPU devices, as well as the split weights. And then if we actually do the matrix multiplication here, we get 0, 1 onto 1020, 2, 3 onto 1020, 4, 5 onto 1020, and 6, 7 onto 1020. And for the first value, you just get 20. You can do this multiplication. I did this actually on my own, literally column by column to verify for myself before recording this video. So if this is something which you think will give you more intuition, then I highly recommend. At least it helps me. So if you want, do that multiplication, you'll see, and then we concatenate the two columns and get the same result as we got previously. Now, there is a code implementation which we're skipping, and the second option, of course, is along the row, so row-wise sharding or row linear, and this means that we split the weight matrix into chunks of rows. However, this also requires us to split the inputs, which need a scatter operation rather than a broadcast, as used in column linear sharding. And it's a scatter because we're not giving all GPUs everything, we're just giving all GPUs something, whereas a broadcast gives everything from one device to everything else. In this case, we are just giving one column of the inputs to every GPU instead of the entire input. Let's get back to here. The result on each worker are already in the right shape at the end of the computation, but they need to be summed for the final result, thus requiring an all reduce operation in this scenario. All reduce just being sum. We're reducing two matrices down to one. So what we do here is we have a 4x1 and a 1x2, which gives us a 4x2. And in this case, we're actually just doing a single multiplication between the elements in this column with this row. So 0, this is why the first row, for example, is 0, 0. Check this for yourself to see that you get the same result. And once again, the primitives are scattering onto the two devices and then all reducing onto whatever the root device is after the operation has been completed. And once again, if you want to see this implementation in code, then be my guest. It's on the Ultra-Scale Playbook. So that was in the theoretical or on the toy example stage. Now we're going to do it on a real model, which is the transformer. So we have the fully connected pointwise feed-forward neural network, as well as our multi-head self-attention, and we can apply tensor parallelism to both of these cases. So the feed-forward part can be parallelized by having a column linear followed by a row linear, which amounts to a broadcast to copy the input and an all reduce in forward. And one thing that's interesting is that a broadcast is indeed an actual training where we can make sure inputs are already synced across TP ranks as we go from the large projection matrix to the down projection matrix. So between these steps, we actually don't need to have any communication between the matrices. That is to say, between the 4x and the 4 down, there is no requirement to communicate between the devices, and I'll show you why. And we're first going to look at a naive implementation, which I drew myself, and then the optimized version. Okay, so here you have the naive, fully connected, pointwise, feed-forward neural network tensor parallelism, which I drew a few hours ago. And let's look at our inputs. So we have our input matrix X, which is batch times hidden dimension. And you may be wondering, where is the sequence length? Because normally it's batch times sequence length times hidden dimension. Well, in this case, since we're only performing the projection on the hidden dimension, we combine the batch and the sequence length into one parameter, even though within the memory that is managed by PyTorch, there are still different definitions for each dimension. In this case, we just simplify it like this, such that all of the sequence lengths are concatenated one along the next. So in this case, we have H, and then if the batch size is 4, that means we have S1, S2, S3, S4 along the batch dimension, because we are essentially flattening the cube into a 2-dimensional matrix with hidden dimension as one dimension and batch sequence as the second. So this is our input. And then of course, the initial matrix that up projects our values from our residual stream, we can just consider that to be a 4x increase from hidden dimension to 4h, or just f, which is what I put it as. And then we split it column-wise at the very beginning. So this is important. And p is just the number of splits. So since we do a 4x increase, I thought it's more convenient if we also set p to 4, because then we'll get some nice division. In this case, the column-wise split weight matrix would be h by f divided by p, because we're splitting it up into 4 pieces column by column. So this matrix here, which is the up projection matrix, would be split up 1, 2, 3, 4. And this is one piece of it, which would have dimension h by h, because we divide f by p, which in this case is 4. And then we do our matrix multiplication. So on each device, we multiply x by wp, which gives x prime. And this is the same thing, or in terms of the dimension output, it's b times f divided by p. And then in the naive implementation, we would do a reduced scatter, which is to say that W1, W2, W3, and W4 would share their outputs, or rather device 1, 2, 3, and 4 would share their outputs in order to combine them again and concatenate them, just as you remember in the first example when we concatenate the matrix, the 2 columns that were 4 by 1 and 4 by 1. In this case, we would also concatenate them, and then we would have a final dimension of b by f, because we have quadrupled the hidden dimension length. And this is in the naive implementation. In the more optimized version, there's actually no need for communication here. But anyways, let's continue in the naive way. Okay, so we've done the up projection. Now we need to do the down projection. So we're going to start here. X prime is b times f, just as we have here, because we have f divided by p columns. So, sorry, we have p f divided by p columns. So p times f divided by p is just f. So this is the dimension of x prime. And then w prime, of course, maps from quadruple to the normal hidden dimension length, which is from f to h, or from 4 to 1 if you want to have the ratio in mind. And now we have to split up both our inputs and our weight matrix, because if you remember, when we do the row-wise sharding, we have to split up both matrices. So in this case, we get back our b times f divided by p columns, which is why, in fact, we can just completely avoid all reducing, because since we reduce scatter and then get back the same value afterwards, then you just don't need to do the communication. And then we also have our w prime p, which is f divided by p times h, or just h by h, so it's the same size. It goes from f divided by f times h, and then we split up it row-wise, which is important, and we just get a h by h. And therefore, if you do the dimensions, we have b times f divided by p times f divided by p times h. So we just get b times h, which of course is our input, because in the MLP layer, in a transformer, the input is the same as output. Dimension-wise, of course, the values change, but the input dimension is the same as the output dimension. And then if we come all the way over here, you can see how the multiplication occurs mechanistically. So we have x1 prime times w1 prime, x prime 1 meaning the first column of the sharded input slash activation, times w prime 1 meaning the first row of the sharded weights. And this gives us BH. Once again, as I described, we have the same inputs and outputs, active dimensions, and then we have to sum up y1 to y4 because we split up into p equals 4 shards. And then if we sum up these 4 matrices, then we return our final answer y, which is the result of our up projection and down projection in the feed forward layer. So we saw the naive implementation. Now I will quickly go through the efficient implementation, which is to say that for the up projection, we will split our weight matrix column-wise, and then this will give us only p columns, p equals 2 in this case. So we have 2 devices, and we split up the weight matrix into 2 pieces. This in general is helpful to split up in the same amount of devices that you have. And then since we need to split up anyways for the row-wise sharding by column, we don't do any communication here and just complete this multiplication, and then all reduce into our final answer, which is the same input dimension as the output dimension. So that's very practical. Now we can generally follow a similar approach for attention, where QKV matrices are split in a column parallel fashion, and the output projection is split along the row dimension. With multi-head attention, the column parallel approach actually has a very natural interpretation, which is to say that we're using multi-head attention, but each GPU actually computes the attention for an individual or a subset of heads, which is to say that we need to either have the exact number of heads equal to the number of GPUs, or it has to be a factor of that, which is to say that if there's 8 heads, we can either have 1, 2, 4, or 8 devices in order to have a seamless tensor parallelism output. The same approach also works for multi-query and grouped query attention, where keys and values are shared between queries. However, the tensor parallelism degree should not exceed the number of QKV heads because we need intact heads per device. Otherwise, we cannot compute the attention heads independently on each GPU, and we'll need to have extra communication. So for group query attention, where each query matrix corresponds to a group of keys and values. So if you have a group of, for example, 2 key and value matrices for every 1 query matrix, then the TP degree should actually be smaller than the number of KV heads and should be equal to the number of query heads. For example, Llama 3.8b has 8 key value heads, so the tensor parallelism degree should not exceed 8. And in fact, it should be equal to the number of query matrices. There's definitely some ambiguity here, which the authors would definitely need to review. So if I were you, I would definitely encourage writing in the forum about this section here, because it's not really that well done. So before I go through the pebble graph of attention, let's just see what ChatGPT explained how it works in terms of tensor parallelism over attention. So first, we do a column parallel, splitting the heads over the Q, key, and value matrices so that each GPU has its own slice of attention. And then for the row parallel output, we split the final projection so each GPU does just its own slice. And we all reduce only once at the very end to remerge the partial outputs. One thing worth noting is that since we are only doing a factor of the number of heads, no head is ever on one GPU and half on another. We only shard whole heads, keeping each head's QKV entirely local to that device. So going through this graph here, we begin by doing a column-wise shard over the attention heads for all 3 query value and key matrices. And then we will do this product between the query and key matrices, a softmax dropout. And then similarly with the V1 matrix, we will do this all locally, so there's no need for sharding within the device itself. And then we will do the row-wise sharding for our output projection. So of course, this inside part with the dotted lines represents our self-attention. But once we come outside, we are multiplying our attention matrix with the output projection matrix using the same row-wise sharding that we saw here. So the first attention calculation, the attention calculation itself, scale dot product attention, which is KQT softmax times V right here. This happens with the column-wise sharding, and then the row-wise sharding occurs on our output projection matrix. And then we do an all reduce to consolidate the attention scores, because we did use the row-wise sharding, which requires an all reduce. And then at this point, we can do dropout, layer norm, etc. And let's finally note that tensor parallelism is not a silver bullet for training. We've added several distributive communication primitives directly in the computation path of our model, which are therefore hard to essentially overlap with computation, like we did with the zero redundancy optimizer. So our final performances will be the results of a trade-off between computation and memory gains and the added communication overhead. And to illustrate this, let's look at the graph of computation versus communication for a single GPU. So we first have layer norm, which is pre-layer norm, and then we apply our MLP layer, FC1, GELU, FC2. So this is the activation function, and these are the up projection and down projection matrices. And then this is only done for a subset of our weight matrix. So we all reduce to gather these across the GPUs. And then we have another layer norm. Looking at the timeline of operations in TP-MLP, which is similar to attention, we can better understand the trade-offs involved. In the forward of each decoder layer, we hit a synchronization point with the all-reduce operation that cannot be overlapped with computation. This exposed communication overhead is necessary to combine partial results across tensor parallel ranks before the final layer norm can be applied. So they do say this, but then they mention that in the Megatron LM Nanotron implementation, a partial overlapping of all gather with FC1 computation does occur, which is to say that the all gather and the next FC1 are overlapped. So apparently, and in further work such as Domino, there is a way to maximize this overlap. So in essence, disregard what they say here, it is still possible to overlap communication and computation to reduce idle time. And usually this happens by either moving things by prefetching while computation still occurs, or while communication occurs, doing some type of pre-computation. Moving on, tensor parallelism does, of course, help reduce activation memory. This was the whole reason it was introduced for matmols, since the intermediate activations are sharded across GPUs. However, we still need to gather the full activations for operations like layer norm, which means we're not getting the full memory benefits we could. Additionally, tensor parallelism introduces significant communication requirements that heavily depend on the network infrastructure, and the inability to fully hide this particular all reduced behind computation means it directly adds to the critical path of forward propagation. And I think that's just fancy talk for saying that it decreases throughput. And this is what it shows here. So as we scale tensor parallelism, the throughput decreases quite a lot. But one thing worth noting is that we are able to increase our maximum batch size because we are splitting the activations across our devices. In practice, as we see on the left plot, the communication overhead of tensor parallelism becomes particularly noticeable as we scale beyond 8 GPUs. Why is this the case? This is because tensor parallelism within a single node, which is usually 8 GPUs, can use NVLink. But then as soon as we go across nodes, there's only slower network communication protocols available. And this is why we observe significant drops when moving from 8 to 16, and an even bigger one from 16 to 32. That being said, tensor parallelism provides important benefits for memory usage by distributing model parameters, gradients, optimizer states, and activations across GPUs. And for a 70 billion parameter model, when we have no tensor parallelism, we can see that because we're having a copy of the models, parameters, gradients, optimizer state, and activations across every GPU, we can't even see all of the types of memory consumers. With 8 GPUs performing tensor parallelism, we can see that our optimizer state is taking up a lot of memory. This is because, of course, the optimizer stores both the momentum and variance in 4 bytes. But anyways, once we go to tensor parallelism with 16 nodes, 16 GPUs, which would be 2 nodes of 8 GPUs, we can see that we can at least fit a model of 1,000 or 4,000 sequence length into these 2 nodes for training. So it's better than nothing. We've seen that layer normalization and dropout still require gathering the full activations on each GPU, which negates the memory savings. But can we do better by finding ways to parallelize these remaining operations as well, which would mean that there would be no need to have intermediate all reduces, which is what causes this memory bottleneck. And we will discuss this in future episodes.